This is the analysis for the data that I measured for the specific heat capacities experiment, and I used these specimens, lead and brass, and these were hot specimens and cold water. I only chose to do one of these here. Notice that further down you have the same one, hot specimen, cold water, but then of course there's the other one, the specimen, the metal in the freezer, and then drop it into hot water. Either way, the analysis is exactly the same, so I get away with just showing you one particular example. Okay, for the lead, I measured a mixing temperature of 13 degrees Celsius, and it was an initial temperature of 99 degrees Celsius. So TF minus T final is negative 86 Celsius degrees. I'm going to copy this negative sign here, just makes it look a little better. The mass I had mentioned in the video was 361 grams. I had determined that at another time. And then the specific heat capacity of lead I looked at it as 128 joules per kilogram and Celsius degrees. And then I have to multiply this one times that according to the equation for the heat flow, paying attention that I need to convert the 128 joules per kilogram and Celsius degrees to joules, grams, and Celsius degrees, which means when I type it in on my calculator it's 0.128. So that's what I'm going to do, 0.128 times a mass of 361 times temperature change of negative 86 Celsius degrees, and I come up with 3,973 joules. And then I look at significant figures. There need to be 2, so these are my significant figures, but the 7 of course rounds up to 4,000. And here this one is actually 2 significant figures. These 2 are significant, the other 2 zeros here are placeholders. I know it doesn't quite look that way, that both of these are significant, but we know that from the context, from that we measured here 2 significant figures, making this here a 4,000, not around at 4,000, but it's not 3,900 or 4,100, but it really is 4,000. Okay, water. Mixing temperature, of course, 13 degrees. It was cold water. There was ice in the beaker that I had used to make the water as cold as possible, and that was 4 degrees. 13 minus 4 is 9 degrees. That's a positive number. That's the temperature increase for the water. And then the mass for the water, I said 100 milliliters, and that would make 100 grams because of the density of water to be 1 gram per milliliter. And then the specific heat capacity of 4,186 joules per kilograms and Celsius degrees. So again, on the calculator I would type 4.186 times 100 times 9, and I come up with 3,767. That should be rounded to 4,000 because of the one significant figure right here, but I'm going to make an exception here, and I'm just going to round it to 2 significant figures as well, so we can see a little bit of a difference there. So that should be 3,800 rounded. And oops, I forgot one little thing here. The heat flow came out to be negative. Actually, I have that on my calculator. It said negative 3,973 earlier. And then I'm going to do negative 4,000. I take the absolute value of that, so 4,000 minus 3,800 is 200. For some reason there was that little thing in front, so the difference of the absolute values of these two is 200, and I divide that by, again, the absolute value of 4,000, and I come up with 0.05, and that's an error of 5%. So, and I think you can see that the error between these two is 5%. And again, this is the heat that flows into the water, this is the heat that flows out of the lead. These two numbers should be the same, but because of experimental and measurement errors, they are at least close, within 5%. Okay, for the brass, I measured a mixing temperature of 19 degrees Celsius. The initial temperature for the brass was 99. 19 minus 99 is negative 80. There it is, negative 80. That's actually two significant figures. Look at these two here. Two. It's not 79, it's not 81, it's 80. And the mass, I said that in the video as well, 271 grams. I measured it prior to recording. And then the specific heat capacity, I looked that up for brass, is 380. And when I do the calculations, I plug in 0.38 joules per grams in Celsius degrees times 271 grams times negative 80 Celsius degrees, and I come up with negative 8238, which I should round to 8,200, negative 8,200 joules that flows of heat that flow out of the brass. For the water, the mixing temperature, of course, is the same, 99 degrees Celsius. It was really cold water at 4 degrees Celsius. 19 minus 4 is 15. And the mass was 100 milliliters, which means it's 100 grams. I mentioned this in the video. The reason why I took 100 grams for the water rather than the suggested 50 is because I had relatively large specimen, and I meant to cover them completely in water. Okay, 4,186 is joules per kilogram Celsius degree is the specific heat capacity. So again, I'm going to type in 4.186 to have it converted to per grams times 100 grams times 15 Celsius degrees, and I come up with 6279, respectively 6,300 joules flow into the water, and we can see these two numbers should be the same, but of course, but due to experimental and measurement errors, yeah, they're a little bit further off than the other one. So I'm going to do 8,200 minus 6,300. Again, the error shows the absolute values of these, so 8,200 minus 6,300 is 1,900, and then I divide that by 8,200, and I come up with 0.23, which means I have an error of 23%. And that's how you analyze the data. And then a reminder, in your conclusion, you have to compare the heat flows, what kind of error you have, and you have to try to explain why possibly do we get relatively large errors at times for the heat flows, and you would have to look at the way the experiment is conducted. I gave you a couple of hints in a post-lab question, and yep, that's how you're going to write your conclusion.